Hi guys, for today's lesson we're going to be dealing with differentiability. So first up, you need to be aware of what the word smooth means in this sort of context of graphs and derivatives and etc. So smooth is a term that describes a function which does not have jagged parts within its graph. So say if you consider this graph y equals the absolute value of x, these lines mean the absolute value, i.e. this is another way of representing this function. So y is equal to negative x, which is like a straight line with a gradient of -1 when x is greater than 0. Or y is equal to just a positive x, so that's got a gradient of +1 when x is greater than or equal to 0. Sorry, a bit of a stuff up there. That's got to be less than 0. Okay, so this is what our graph looks like. So we can see here that our negative x part is when x is less than 0 over on the left hand side, and we see the negative gradient, the -1 gradient. And this part here, positive x, we can see it's this part here. So this is like our negative x side, and that's like our positive x side. Okay, now do we consider this function to be smooth? Well, we do consider it to be continuous because they join up together at this dot right here. But we consider that like this part would be smooth, like because it's a nice straight line like this. But here, at this point here, it's jagged, it's not smooth. It's very much like not a nice curvy line. It's definitely got this point there. So we say it's not smooth there, but at everywhere else, it's definitely smooth. It's a nice smooth line. So that's the sort of idea of the word smooth. Note, you can algebraically test whether a function is smooth by checking that the gradient is equal where the piecewise function swaps over. So if you check, say for this side of the function, you can check that its gradient is going to be -1, and over here the gradient is going to be +1. So because these gradients are not equal at this point, because over here it's -1, over here it's +1, that suggests that it's not smooth algebraically. That's the way you can do it without just looking at the graph. So let's do an example. Show algebraically that the above function is not smooth. So how do we show this thing algebraically? Well, pretty much we're just going to take the derivative of both of these functions, because smoothness is all about showing that, that the gradients are equal. So the gradient of negative x is going to be -1, and the gradient of x is going to be +1. And we can see that the gradients they're unequal. Like one's -1 and the other one's +1 for these functions when x is equal to 0 at this crossover point. So because these gradients are unequal, it's not a smooth function. Okay, the next word we need to be aware of is the word differentiable. So it's a term that describes whether the gradient can be calculated at a specific x value. So can you find the gradient at different points of a function? Now, we can pretty much define this word, or we can pretty much state a rule that asks is something differentiable or not. So a function is differentiable at a specific value of x, so where x is some sort of number like 0, 1, or 2, like represented by this a, if the function is continuous and the function is smooth at this value of x equals a. So if we want to show differentiability, we need to show it's continuous and then also smooth. Okay, so test each function for differentiability at x equals 0. So here we've got a piecewise function. We want to figure out, well, is this thing differentiable? So for something to be differentiable, it has to tick off that it's continuous, and it also has to tick off that it's smooth. Okay, so the strategy is to test for continuity first, and then test for differentiability. If either fail, then the function is not differentiable. So we need to be doing it at this value of x equals 0. X equals 0 is like this crossover point. So at x equals 0, if we put in the value of 0 into both of these parts of the function, we get that this equals a 3, and we get that this also equals a 3. So it means that this function is continuous. They kind of join up at the same spot. If I show the graph of this, I've put this into Desmos and shown what the graph looks like. You can see that these graphs link up when x equals 0. They link up the point of 3, which we can see is up here. They both equal 3, where they kind of cross over with each other. Like at this point, x equals 0. So that's suggesting that it is continuous. You could draw this graph without lifting your pen. So we've kind of ticked off that this is the case. Tick, the function is continuous. Now we need to show that it's smooth for something to be differentiable. So how do we show that it's smooth? Well, we need to take the derivative of this piecewise function here. So the derivative of x plus 3 is going to be just a 1. So it's for no matter what x is, the gradient's always going to be 1. For this one here, the gradient's going to be 1 take away 2x. Now we want to know what the gradient is at this crossover point. So we need to know what the gradient is when x is equal to a 0. So 1 minus 2 times 0, which is just here, that is equal to 1 as well. So we can see here that this function has always got a gradient of 1. And at this point right here, for the parabola, the gradient is also 1. So that means that we're making a nice smooth transition from this function to this function. It doesn't look jagged here because the gradients on either side of this point at 3 they've got the same gradient of just 1. So therefore we consider it to be smooth because of these equal gradients. Therefore f of x is differentiable because it satisfies that it's continuous, it satisfies that it's smooth. Hope this helps with the questions. Good luck.